Hello my good friends, Derek Deschamps here for Internetworking Influencers, your source for free Cisco certification training for network engineers. Welcome to day 4 of our free CCNA 100-105 ICND1 training course. The Internetworking Influencers CCNA 100-105 ICND1 training course is comprised of 13 videos, each focusing directly on a set of specific items on Cisco's official exam topic list. Today's episode will cover Item 1.8, Configure, Verify, and Troubleshoot IPv4 addressing and subnetting. Item 1.9, Compare and contrast IPv4 address types, including UNICAST, Broadcast, and Multicast. And Item 1.10, Describe the need for private IPv4 addressing. If you would like to have a look at Cisco's official exam topic list, I've included a link to it in the show notes. As a reminder, today's video has a set of free practice questions that are available on our website at internetworkinginfluencers.com that will help you brush up on the topics you learned today. The questions are a true representation of the types of questions you'll face on the actual exam, so be sure to check those out once we're done. Alright, so let's get to it. Now before we dive into IPv4 addressing and subnetting, it is important that you have a thorough understanding of how to convert between binary and decimal formats. Decimal is a base 10 numbering system that uses 10 digits, the numbers 0 through 9, while binary is a base 2 numbering system that only uses 2 digits, the numbers 0 and 1. In binary, each digit is called a bit. With the decimal system that we all know and use daily, the value of each position that a number can take increases by a factor of 10 as we move from right to left. For example, the first position from the right has a value of 1. The second position has a value of 10 times the first position, giving it a value of 10. The third position has a value of 10 times the previous position, giving it a value of 100. The fourth position has a value of 10 times the previous position, giving it a value of 1000. The fifth position has a value of 10 times the previous position, giving it a value of 10,000, and so on. So for example, if we have the number 7 in the first position from the right, we know that this position is worth a value of 1. So to get our total value for this position, we take 7 times 1, which equals 7. If we have the number 7 in the second position, we know the value of this position is 10. So to get our total value for this position, we take 7 times 10, which equals 70. So if we have the decimal number 77, we have the number 7 in the first position and the number 7 in the second position. We take 7 times 1, which equals 7 from the first position, and 7 times 10, which equals 70 from the second position, and add them together, giving us a total value in decimal of 77. The same principles hold true for binary. With decimal, we saw that the value of each position increased by a factor of 10, or 10 times the previous position from right to left. With binary, the value of each position increases by a factor of 2, or twice the previous position from right to left. For example, the first position from the right has a value of 1. The second position has a value of 2 times the first position, giving it a value of 2. The third position has a value of 2 times the previous position, giving it a value of 4. The fourth position has a value of 2 times the previous position, giving it a value of 8. The fifth position has a value of 2 times the previous position, giving it a value of 16, and so on. With binary, we only have 2 digits available for us to use in each position, the numbers 1 and 0. So for example, if we have the number 1 in the first position starting from the right, we know that this position is worth a value of 1. So to get our total value for this position, we take 1 times 1, which equals 1. If we have the number 1 in the second position, we know the value for this position is 2. So to get our total value for this position, we take 1 times 2, which equals 2. So if we have the binary number 1, 1, we have the number 1 in the first position from the right, and the number 1 in the second position. We take 1 times 1, which equals 1 from the first position, and 1 times 2, which equals 2 from the second position, and add them together, giving us a total value in decimal of 3. So now let's look at a full example of how to convert from binary to decimal. If we want to convert the binary number 10110 to decimal, we write out our binary number with the position values written above. To write out our position values, we start with 1 on the right, and fill in each of our values by doubling the value of the previous position. So our first position from the right is worth a value of 1. Our second position is worth a value of 2. Our third position is worth a value of 4. Our fourth position is worth a value of 8. And our fifth position is worth a value of 16. Now to get the value of our binary number in decimal, we need to calculate the total values for all positions that contain a 1. And add them together. We can safely ignore the positions that contain a 0, as 0 times the position value will always equal 0. So in this case, we take 1 times 2, which equals 2 from the second position, and 1 times 4, which equals 4 from the third position, and 1 times 16, which equals 16 from the fifth position, and add them together, giving us a total value in decimal of 22. To convert decimal to binary, we work through a similar process, only in reverse. So for example, if we wanted to convert the decimal number 22 to binary, we would begin by writing out our position values. To do this, we start with a position value of 1 on the right, and then for each position, simply double the value of the previous position. We continue doing so as long as our position value is less than or equal to the decimal number we want to convert. In this case, we would write out our position values to 16, since the next position value would be 32, which is greater than the decimal number we want to convert. We then treat the decimal number we wish to convert as our remainder, and move from left to right, placing a 1 in the first position that has a value of less than or equal to our remainder. In this case, the first position value starting from the left that is less than or equal to 22 is 16. So we place a 1 in the position with a value of 16 and subtract 16 from our remainder, leaving us with 6. We continue moving from left to right, looking for the next position value that is less than or equal to our new remainder of 6. In this case, it's 4. So we place a 1 in the position with a value of 4 and subtract its value from our remainder, leaving us with 2. We continue moving from left to right, looking for the next position value that is less than or equal to our new remainder of 2. In this case, it's 2. So we place a 1 in the position with a value of 2 and subtract its value from our remainder, leaving us with a remainder of 0. We now fill in any remaining positions with the number 0, and we now have our decimal number in binary. In this case, the decimal number 22 is equal to 10110 in binary. Now that we are all up to speed on decimal and binary, let's take a look at IPv4 addressing. An IPv4 IP address is a unique 32-bit number that can be used to identify each network interface on a network. To make IP addresses more readable to humans, the 32 bits are divided into 4 octets, or groups of 8 bits. Each octet is represented by a decimal number ranging from 0 to 255. For example, if we take this 32-bit binary IP address and divide it into 4 octets and convert each octet from binary to decimal, we get the IP address 192.168.0.1. An IP address is comprised of 2 parts. The network address portion of an IP address identifies which network the IP address belongs to, while the host address portion is used to identify the individual host or interface on that network. The network address portion is used by both hosts and routers to determine where to forward packets. For example, if a host wants to send a packet to another host, it compares its own network address with the network address of the destination host. If they both have the same network address, the host knows it can communicate directly. If they do not have the same network address, the host then knows they are not on the same network and forwards the packet to its default gateway. Routers also use the network address to determine where to forward packets. When a router receives a packet, it compares the network address of the destination host with the information in its routing table to determine where to forward the packet. A subnet mask is a 32-bit number that is used to differentiate between the network address portion and the host address portion of an IP address. To show you how this works, let's use a subnet mask of 255.255.255.0 with the IP address 192.168.0.1. To differentiate between the network address portion and the host address portion of the IP address, we convert both the IP address and subnet mask to binary and line them up in a table. The positions that contain a 1 in the subnet mask signify the bits that belong to the network address portion of the IP address, while the positions that contain a 0 in the subnet mask signify the bits that belong to the host address portion of the IP address. In our example, we can see that all the bits in the first 3 octets belong to the network address portion of the IP address, while all the bits in the last octet belong to the host address portion of the IP address. The network address is always the first address on a particular network. If we want to calculate the network address, we simply set all bits in the host address portion of the IP address to 0. We then convert each octet back to decimal. In this example, our network address is 192.168.0.0. A broadcast address is used for sending packets to every host on a particular network, and is always the last address on that network. If we want to calculate the broadcast address for a network, we simply set all bits in the host address portion of the IP address to 1. We then convert each octet back to decimal. In this example, our broadcast address is 192.168.0.255. As I mentioned, the network address is always the first address on a network, and the broadcast address is always the last address on a network. This means that if we know the network address and the broadcast address, we can then determine the IP address range that is available to use for hosts on that network. In this example, since our network address is 192.168.0.0, and our broadcast address is 192.168.0.255, we know that the IP addresses between those two numbers are available to use for hosts. In this case, the range 192.168.0.1 to 192.168.0.254. This gives us a total of 254 IP addresses available to use for hosts on this network. The number of bits used in the subnet mask to identify the network address directly affects how many bits are available to identify hosts on that network. This means the longer the subnet mask, the smaller the network. In this example, a subnet mask of 255.255.255.0 signifies that 24 bits are used to identify the network address, leaving us only 8 bits to identify hosts on that network. 8 bits allows us a maximum of 2 to the 8th IP addresses, which is equal to 256. As we just saw, the first IP address on a network is always used for the network address, while the last IP address is always used for the broadcast address, meaning we now have a maximum of 256 minus 2, or 254 IP addresses available to use for hosts. In general, the maximum number of IP addresses available to use for hosts on a network is equal to 2 to the h minus 2, where h is equal to the number of bits in the host address portion of the IP address. Public IP addresses are globally unique IP addresses, used by hosts and devices that need to be accessed from the Internet. Public IP address allocation is managed by the Internet Assigned Numbers Authority. Examples of hosts and devices that would use a public IP address are web servers, external DNS servers, external mail servers, external routers, and firewalls. Private IP addresses are IP addresses that are reserved for private networks and are not routable on the Internet. A private IP address is used for communication within an internal network. Private IP addresses must be translated to a public IP address before communicating with external hosts. Examples of hosts and devices that would use a private IP address are end-user systems, internal servers, and internal routers and switches. There are 3 IP address ranges that are reserved to be used on private networks. The first range is from 10.0.0.0 to 10.255.255.255. The second range is from 172.16.0.0 to 172.31.255.255. And the third range is from 192.168.0.0 to 192.168.255.255. The IPv4 address space is divided into 5 classes. You can identify the class of an IP address by looking at its first octet. A Class A IP address has a first octet of 1 to 126. A Class A IP address has a default subnet mask of 255.0.0.0 and is generally used for large networks. A Class B IP address has a first octet of 128 to 191. A Class B IP address has a default subnet mask of 255.255.0.0 and is generally used for medium-sized networks. A Class C IP address has a first octet of 192 to 223. A Class C IP address has a default subnet mask of 255.255.255.0 and is generally used for small networks. A Class D IP address has a first octet of 224 to 239 and is used for multicast communication. A Class E IP address has a first octet of 240 to 255 and is reserved for future use. It is also important to note that IP addresses with a first octet of 127 are reserved for loopbacks. There are a few types of IPv4 addresses that you need to be familiar with for the exam. The first type of IPv4 address is a unicast IP address. A unicast IP address is a Class A, B, or C IP address used to uniquely identify each network interface on a network. A unicast IP address is used when sending packets to a single receiver. The second type of IPv4 address is a broadcast address. A broadcast address is the last IP address on a network. Packets sent to the broadcast address of a network are delivered to all hosts on that particular network and are often referred to as directed broadcasts. A special broadcast address exists called the local broadcast address, which is the IP address 255.255.255.255. Packets sent to the local broadcast address will be delivered to all hosts on the local network of the sender. Unlike directed broadcasts, routers will not route packets destined for the local broadcast address. The last type of IPv4 address is a multicast address. A multicast address is a Class D IP address, used to identify a multicast group. Packets sent to a multicast IP address will be delivered to all hosts in that multicast group. Hosts can join multicast groups by notifying their local routers. There are times when a Class A, B, or C default subnet mask may not be the right size for the number of networks or hosts required. This is where subnetting comes in. Subnetting is the act of dividing a single Class A, B, or C network into smaller logical networks. Each link that is separated by a router requires its own unique network address. So for example, on this network, we would require 4 unique network addresses, one for each link that is separated by a router, and which we can see here highlighted in red. However, what if we only had the one Class C network, 192.168.0.0, with the default subnet mask of 255.255.255.0 available to use? The simplest method to solve our problem would be to divide our Class C network into 4 equal-sized smaller networks, or subnets. Since the largest network on the diagram contains 40 hosts and one router interface, we will need to ensure that each of the 4 new subnets has a minimum of 41 IP addresses available to use for hosts. To achieve this, we need to borrow bits from the host address portion of our Class C network to be used as subnet bits to identify our 4 new subnets. The number of bits we borrow for subnet bits will determine the maximum number of subnets we can create. However, when borrowing subnet bits, it is always a balance, as the more subnet bits you borrow, the less host address bits you have to define IP addresses on those subnets. So let's determine how many subnet bits we need to borrow to identify our 4 subnets. The maximum number of subnets we can create is equal to 2 to the s, where s is equal to the number of subnet bits. If we only borrowed 1 bit and set s to 1, that would only give us 2 subnets, and we require 4. If we borrowed 2 bits and set s to 2, that would give us our required 4. So now we know we would need to borrow 2 bits from the host address portion of our Class C address to be used as subnet bits to identify our 4 new subnets. So let's calculate the subnet mask for our 4 new subnets. To do this, we write out the original subnet mask in binary and identify the host address portion by looking for the bits that are set to 0. We then borrow the 2 bits from the host address portion of the subnet mask to be used for subnet bits and change each of their values to 1. Once we convert each octet back to decimal, we get the new subnet mask for our 4 new subnets, which is 255.255.255.192. Now we need to ensure that we have enough host address bits left over to be used to define the IP addresses for our hosts. We can see that after borrowing the 2 subnet bits, we now have a total of 6 bits to be used for host address bits. As we covered previously in this episode, the maximum number of IP addresses available to use for hosts on a network is equal to 2 to the h minus 2, where h is equal to the number of host address bits. This means our 6 host address bits gives us a maximum of 2 to the 6th minus 2, or 62 IP addresses available to use for hosts. Since we only require 41 IP addresses in our largest subnet, this will meet our needs. The network address of a subnet is often referred to as a subnet ID. To calculate the subnet IDs of our 4 new subnets, we write out the original subnet mask and original Class C network address in binary. We then identify the host address portion of our network address by looking for the bits that are set to 0 in the subnet mask. We then borrow the 2 bits from the host address portion of the network address to be used for subnet bits. The first subnet ID is the easiest to calculate, as it is always equal to the network address of the original network. This means our first subnet ID is 192.168.0.0. To calculate the remaining 3 subnet IDs, we now simply increment the borrowed subnet bits in the network address. Incrementing the subnet bits in binary gives us our second subnet ID of 192.168.0.64. Incrementing the subnet bits again gives us our third subnet ID of 192.168.0.128. Incrementing the subnet bits again gives us our fourth subnet ID of 192.168.0.192. Another way to express a subnet mask is by writing a slash followed by the number of binary ones in the binary subnet mask. For example, the subnet mask of our four new subnets, 255.255.255.192, consists of 26 ones when converted to binary. Rather than write out the full subnet mask, it could be expressed as /26. The four new subnets could then be written as 192.168.0.0/26, 192.168.0.64/26, 192.168.0.128/26, and 192.168.0.192/26. This way of expressing a network is called classless interdomain routing, or CIDR notation. Our original Class C network has now been divided into four equal-sized subnets: 192.168.0.0/26, 192.168.0.64/26, 192.168.0.128/26, and 192.168.0.192/26, each containing a total of 62 IP addresses that can be used for hosts. I should also point out that any of those subnets could now be further divided using the same process if required. For example, 62 IP addresses is a bit too many for the transit link between the two routers. So if we desired, we could further divide its subnet into smaller sized subnets in order to conserve IP addresses. Having a thorough understanding of binary and how an IP address is divided into network address, subnet, and host address portions is key to successfully completing the subnetting questions on the exam. There are many shortcuts and tricks out there to help speed up your calculations. But before using any of them, I'd highly recommend you learn and become efficient at doing subnetting in binary. This way you'll have a thorough understanding of the concepts and be ready for any questions Cisco can throw at you. I'd also highly recommend you look over our free practice questions to become familiar with the many different ways subnetting questions can be asked. And that brings us to the end of Day 4 of Internetworking Influencers CCNA 100-105 ICND1 training course. Don't forget to complete the free practice questions for today's material, which can be found on our website at internetworkinginfluencers.com. The free questions will help highlight the key points that Cisco will expect you to know for the exam. Also, if you enjoy our free training and would like to show your support, please check out our Patreon page. We offer numerous perks to our supporters, ranging from additional practice questions and detailed study notes for each video, to direct access to our instructors to answer any questions you might have. I'll be back next time for Day 5, where I'll cover IPv6 addressing, concepts, and implementation. I'm Derek Deschamps for Internetworking Influencers. Thanks for watching.